Yeah, yes.
I've never been to the Middle East. That's
Oh.
one area I've never been to.
It's, you know, everywhere I go, I learn.
Oh, that's right.
Yeah,
That's right.
that's not, it is just, I don't know.
There we go. Awesome. Thank you, Mom.
Yeah, no problem.
Yeah.
Okay, folks, I'm going to go ahead and get started. I know there's a couple of people that need to leave early. I would recommend chowing down on the donuts as quickly as possible. We get a nice sugar buzz out of that as well. So, right, so thank you very much for attending. I know the donuts weren't the big draw. Everybody has kind of an intrinsic interest in nonlinear transformations of data. So I thought that was going to be, you know, bring everybody in and fill up the room. So thank you, guys. So let me just give you some honest background here. I'm easily confused, and if you don't believe me, you can ask my wife. Occasionally that serves me well in the sense of when I read journal articles in the methods sections and the results sections, I oftentimes have questions about why people are doing things the way that they do them. And I had some luck with that in an earlier project where I was looking at the use of control variables in research, and that ended up to be a fairly decent article, or at least cited quite often. I'm not sure good article and cited often are the same thing, but anyway. So this is kind of another example of that, where I would read through an article in my area, organizational research, and I'll see certain variables in the article that are treated differently than others. And so one way that's fairly common to see variables treated is an author will say something like variable X was skewed or leptokurtic, you know, non-normal in some sense, so we took the log, or we did a square root or something. And that's actually one of the better explanations, because a lot of times, as you'll see, there was no explanation for why variables were transformed, which is even a little more weird for me. So I think, when I think back on my own training in graduate school, we had all kinds of stat classes, but we didn't really have in any of those classes a discussion of when and how you should transform variables, what you can expect to accomplish from doing so, and what transforming will not accomplish. So I wanted to talk a little bit about a project today that I've been working on in that respect. So some of the questions that I had, you can see up here. These are questions I had just from reading articles, and I'd see transformations done. And so I'd say, well, variable X was log transformed in this article, but here's the same variable X, no transformation. I'm not sure why that is. Why is it that of all the possible nonlinear transformations you can have, and there's literally, you know, a dozen or more, why is it always a log? You can take a square root, you can square, you can cube, you can take, you know, all kinds, but it's always a log. That led me to have a suspicion, and that suspicion was that, as in other areas in my field, sometimes there's these statistical myths that are generated. And one myth that I had investigated earlier was with control variables. The myth there was if you just throw in a bunch of control variables, somehow you purify the relationship among variables and magically divine the truth. I think the myth that I'm beginning to have here with nonlinear transformations is if you got a non-normal distribution of some kind, you just take the log and everything's going to be cool. You know, your skewness will go away, it'll be normal in other ways, you get the right correlation among variables and so on. So anyway, that's kind of my starting point, was just basically, I don't understand. And the truth is, not to get on my high horse, I've done the same thing myself. In other words, there's a paper right now in press where we took a log of a variable. It was before I started thinking about all this. It's like 2 years ago this paper was written. And it's like I took a log of a variable, and now I'm thinking back on it going, geez, you know, Nobody objected. We thought it was the thing to do. It reduced the skew, but I'm not sure that's the greatest explanation. So it's not like I think I knew what I was doing. I'm definitely a part of the problem if in fact there is a problem. So in order to examine a little more systematically whether or not this was an issue in management research, we did a study where we did a stratified random sampling of 323 articles over a period of 5 years in our top 6 journals. And I guess I should give credit where credit's due. Bob Vandenberg and Melissa Roberts at University of Georgia were also involved. So we got all these articles from the top journals, and we developed a coding sheet for coding how the variables were treated, what explanations were provided, what sort of data was reported, and so on, just to kind of see what was being done. Trying to be good researchers, we also double coded a number of the articles to make sure that the coding scheme was reliable. And there was a lot of agreement. We went back and forth until we had a coding scheme that we could all agree, okay, we read this article, they did this to that variable and reported this and so on. So anyway, as you can see there, the agreement was pretty good once we got to the final version.
Do you intend to have your PowerPoint up there?
Sorry?
There's nothing up there.
Wow. Where's Marty? Okay, I thought he had set it up already.
Source.
Yeah. That kind of makes a difference.
The PC, that should.
This should go house here, PC. Where is it? There it is. That's going to make a lot more sense, guys. All right. So I just said that, and now we're here. So we have these 323 articles, and you can see kind of a quick summary of what we found descriptively. 38% of the articles included at least one nonlinear transformation. So it's non-trivial. It's not like you find it in every article, but in a fair proportion. Oftentimes, independent variables were transformed, control variables, CVs, and even dependent variables, which, in our literature, it's been argued that, nonlinear transforming dependent variables is often questionable for a variety of reasons that I won't get into right now. 88.8% of the transformations were logs. So we did have a few that were square roots and others, but it was almost all logs, which I thought was interesting because the way that implies that the nature of the non-normality in distributions is, basically the same, because the log is going to have a different effect on a distribution depending on what it looks like to begin with. So again, I thought that was a little confusing, but we shall see. Not surprisingly, the kinds of variables that are transformed are ones where there are kind of counts, right? So you're going to see a skew where, for example, in an example I'll give you in a little bit, let's say you're measuring absenteeism. A lot of people won't be absent at all over a period of, let's say, a week. So some people will be absent maybe once or twice, and then there's going to be a small number of people that are absent a lot. So you get a very skewed type distribution on these kinds of variables. So size, number of employees, age, sales, etc. So then using our coding sheet, we just tried to identify, in this case, the justification that was provided. So we had these categories, no rationale, correct for skewness, etc., that we had identified ahead of time. And then for a given article, we just marked what was the reason. So in over half the cases, there was no reason at all given for the nonlinear transformation. And it's even worse than I'm making it sound. I mean, there are cases in top journals where you don't see anything about a nonlinear transformation until you get to like table 2, and all of a sudden it's log X out of nowhere. So that definitely does happen. Correct for skewness, when an explanation was given, that was almost, well, by far the most common. It was skewed, so we took a log. It was skewed, so we took a log. A little more extravagant claim for taking a log or any other nonlinear transformation is we're going to normalize the distribution. Wow. So, I mean, that's saying a lot, right? That's not just skew. If it's leptokurtic or platykurtic, we're going to fix that. Whatever it is, it's not perfectly normal. We're going to make it normal by doing a log. I don't know if you've ever played around with the data and looked at what happens when you take a log, but it doesn't automatically normalize a distribution. So I'll give you some specifics on that a little bit later. And then reducing heteroscedasticity, easy for me to say. As you guys know, heteroscedasticity is simply where the residuals for a variable are larger at one value than they are for another, right? So it's not a uniform distribution of residuals. It's like really big on this end of the scale and then smaller on another end of the scale. So, yeah.
How many of the 50%, did you check if any of the 50% say, we're doing this because somebody else did it?
Yeah. One coding that we have that I didn't report here, but I've got in the paper, is citations. You know, did they provide a citation? And there are very few of those. So, I mean, at least that would be like, we did it because they did it. Of course, that's not always the best explanation, especially when you have something that you suspect might be a myth. You know, we did it because they did it could just be perpetuating, you know, kind of not that great of a practice. So, but at any rate, yeah, not too often. In terms of reporting, you know, so we were interested in not just what kind of reasons were provided for nonlinear transformations, but how were they reported, how were they interpreted. So given that a common reason for, say, logging a distribution was to reduce skewness, you would think there would like perhaps be a sentence saying, and we looked at skewness after the transformation and the skewness was less, right? Something where you would say, we did it for this reason, and then see skewness is less afterwards than there was before. But as you can see, in 97% of cases, there was no information provided about the effects of performing the nonlinear transformation on the original distribution. Another issue is, in my field at least, I suspect perhaps yours as well, the reliability of measures is really important. Because as the measure of a given variable becomes more unreliable, the nature of that and magnitude of that variable's correlation or association with other variables changes, right? So that's just as true for a variable that's non-linearly transformed as for any other variable. And there were no cases where the reliability for an NLT was reported. Yeah, so I thought that's kind of interesting. Now you might say, well, if you're dealing with archival data, reliability is not really an issue. Reliability, if let's say I'm measuring height or cognitive ability or something like that, well, you see, reliability, you do a test, retest kind of reliability, or if it's a scale measure on a survey, you calculate Cronbach's alpha or something, right? But maybe it's not so relevant for archival data. But then there's a whole literature on why archival data can be lacking in reliability. I didn't actually know that because I don't do that much archival data study. But even with data sets like CompuStat that are so widely used, there's articles on problems of reliability among these measures. And they're just not reported. At least they're not reported in my field. Okay. Now, another thing that can happen, if you take a nonlinear transformation, it can change your results such that, let's say, for example, the correlation between job satisfaction and absenteeism is not significant when absenteeism is measured in its raw score form. But you take the law of absenteeism, and now there's a correlation between job satisfaction and log absenteeism, see? So this is kind of an important issue. And it would be, I thought, you know, it would be nice to know, well, did doing the transformation change the results? Kind of like in the way I just said. Because if you don't know that, you don't know what the original results would have been. What was the effect of the transformation? So anyway, 95% of cases, there was no report of the effect of the transformation on the results. Okay, so I'm going to skip the next bit. There's problems in the way NLTs are labeled and reported. This is perhaps a little more trivial, but it's really confusing in an article if an author says, we're taking the log of variable x at one point, and then for the rest of the article, results in discussion question, they just refer to the variable as x rather than log x.
Yes.
Technically, these are two very different variables. They've got different distributions, there's different scores, there's different relationships, there's a different distribution. So, I mean, so calling it, taking the log and then calling it by its original name is potentially confusing, and we saw quite a lot of that. Okay. Here's one other issue I just wanted to broach before I hand out our recommendations. Let's say that you have a hypothesis, x affects y, x affects y, right? And then you log transform y. Now you're not testing your hypothesis. Do you see that? You're testing the hypothesis x affects log y. And so what we see oftentimes in my field is they'll treat the test of x affects log y as the test of x affects y. And it's just not right. I mean, it's just incorrect. So that's one of our major issues in the paper too. So what I'd like to do is, for the rest of this session, is first give you a table of our recommendations. The three of us came up with these based on the study. And then give you a little bit of kind of how we think the process could or should work a little more specifically. So you got the recommendations, which are pretty general, right? And then you've got more specific illustrations of here's how you do it in a way that is consistent with these recommendations. The paper is currently under second review at Organizational Research Methods. So we're working on the revision right now. We're pretty much done with the recommendations, and we're trying to develop these specific illustrations so that doctoral students or anybody else who read the article can say, okay, so this is how we should conduct analysis in a way that's consistent with these. So when it comes to choosing nonlinear transformations, our first recommendation is take a close look at the data. Take a close look at the data to see what it really looks like. Because when you do that, oftentimes the issue is not just skewness, for example. And I think in my field, there's a misunderstanding about the statistical assumptions of many statistical tests. For example, in OLS regression, the F-test assumes normality in the residuals, not necessarily in the original variables, it's the residuals. And one thing that's very clear is you can reduce the skew or the kurtosis of a distribution and have no effect on the residuals. It can still be heteroscedastic, it can still have indications of curvilinearity in the residuals, and taking a log doesn't necessarily have any effect on that. So taking a close look at the data, we think is a good idea. When there's cases of non-normality, there's actually a lot of options that you have now. Other than doing NLTs, you can have Poisson regression. There's a whole set of Bayesian estimators that are now available. And a lot of these, like the Bayesian statistics, don't make any assumptions about normal distributions. So I guess one question I have for a lot of the articles I saw is, okay, well, you had non-normal distribution. Why didn't you use these other techniques instead? I'm not saying necessarily that those techniques are always better, but I mean, you should at least think about them as alternatives. Okay, so I won't go through all of these, but let's just jump down to analyzing for a moment. Consistent with what I was suggesting earlier, we think it's a good idea to examine the transformed data for violations of statistical assumptions too. So not only taking a look at the original data, but once you perform a transformation, look at the data again and see what effects it actually had. Yeah, sure.
So on this point, when you mentioned that they don't do this, so I've generated some made-up data with a positive skewness, did a log transformation, and guess what? It became, so the original data had a positive skewness of 0.5.
Yeah.
After the log transform, it became minus 0.58.
Right.
And actually a square root gave a close to 0.
Yeah, that's right. And I mean, all kinds of examples like that can happen. Another thing that can happen is taking a log or square root or whatever can make a distribution more normal in one sense, but less normal in another sense. So the skews decreased, but the kurtosis increased. I mean, that kind of thing can happen. There's no guarantee that just reducing the skews can have positive effects or is justifiable.
Did you consider the integer values?
Yeah, I only had integer values.
Okay. Typically what happens is when you have a distribution that is closer to Poisson, square root transformation works well.
Mm-hmm.
So something like that may be playing a role there.
But clearly taking log doesn't remove skewness.
No, not
If
at all.
anything, in this example.
There's a great little book. Actually, there's two books that I found helpful in thinking about the types of distributions. Types of transformations you can have. So John Tukey, you know, of Tukey test fame, he had this thing he created called the ladder of powers, and so the ladder of powers identifies transformations that you can take that might pull in an upper tail or pull in a lower tail to the distribution, right? Again, that's only addressing skewness, but if your goal was to reduce skewness, it's not necessarily the log that's going to do it. So I'll just show you real quickly. The ladder of powers would include if you're, okay, so raising each value in a batch to a power less than 1 will pull in a stretched out upper tail. So less than 1 would be, okay, let's see, log is one option. If that doesn't do it, then you take the reciprocal, which would pull it in more. If that doesn't do it, take the reciprocal square. So there's all these transformations that you can take to try to force a distribution to be less skewed. But again, this is only skew. If you wanted to pull it in the other way, you can square, you can cube, you can do whatever you want to it. Whether or not those measures have any meaning in the real world is another question. I mean, for example, if a manager is assessing job performance and discovers through research that that job satisfaction only predicts the log of job performance, I don't know what the manager would do with that information because you'd never observe log performance. You know what I mean? It's just not in the real world. So maybe for predictive purposes, possibly, but for any practical value, oftentimes it's questionable. Okay, so again, I won't go through all these. One thing that we should become standard practice is if you're going to take a nonlinear transformation, at least in a footnote or something, report, here's what the results were with the original variable, here's what they were after we did the log, you know? And if they're the same, if the results were the same, you can even say the results were the same. But if they're different, that begs the question of now which one's right? And which one's justifiable? And why are they different, right? So anyway, we think that ought to be standard practice. All right. Now, another, and this is going to be a recommendation that I think we're going to catch flack for, although not from the reviewers and editor, they seem to love it, but I think we'll catch flack from people who don't like the implications. And that is, if you've got a hypothesis like X affects Y, and then you log or transform a variable, and now you're testing the other hypothesis, X affects log Y, you've now moved into an exploratory mode of analysis. It's no longer confirmatory, right? See what I'm saying? And like any other exploratory mode of analysis, you know, you have to be cautious. And like cross-validating your findings would be a good idea. Treating them as just like you would in like a exploratory factor analysis. You don't act like that's, you know, you're in an exploratory inductive mode, right? So that's our recommendation there. So let me show you just a couple of things regarding the illustrations we're trying to develop to be more concrete about these recommendations. Because without these, this was a comment to the editor, and I think it's true. Without these, see, sometimes I can say a good thing about an editor. That's awesome. So, yeah, so I think the issue's not, all right, now we have these recommendations, we're good to go. It's like, okay, so now what do I do with those? And that's what we're trying to develop now. So this is a little less certain than the previous discussion, but here's where we're headed. So one step is consistent with the first recommendation, is take a close look at the untransformed data to see what it actually looks like. So a lot of times you'll see researchers, they'll just print out a table like this, and they'll say, okay, look, we got a skewed variable, fair amount of kurtosis here. Well, that's fine. And, you know, this certainly bears that out for the variable absent. This is absenteeism. You got a lot of people without any absences, and then you got a few with a lot, like I was saying before. So it's clearly skewed. I think this works. But you ought to take a look at a few other things too. So in this particular data, you've got a bunch of outliers. And one thing I'm not crazy about is when a researcher just drops outliers because they're outliers. There ought to be a consideration of, you know, okay, so these are scores that are beyond the norm. Are they illegitimate for some reason? And in this case, with absenteeism, they're not at all. You don't look at these outliers here and go, oh, we got to get rid of all those for some reason. Those are legitimate data points where somebody was absent a lot. Another thing you can do is look at, let me pull this up real quick. Look to see if there's any curvilinearity evident between variables, because that's another kind of form of non-normality in a sense. We'll take a look at the residuals shortly, but so what we've done here is you've got not just a regression line, but this is the lowest line, LOWESS. So that's a smooth line that is in a sense, a best fitting curve. And what you see there is the possibility of some curvilinearity between satisfaction and absenteeism, because this line here is generally downward sloping, but appears to be somewhat curvilinear. Then, for sure, if you're thinking about doing a nonlinear transformation, you should take a look at the heteroscedasticity issue. And for absenteeism here, you can see pretty clear evidence of it just visualizing the plot. You've got a lot of variability on the low end of absenteeism, and then not very much at higher values. So that's another form of non-normality. And I'll just give away the punchline here. In the data, this data that we're looking at now, we performed a log transformation. We reduced skew and kurtosis, and kurtosis, how peaked or flat the distribution is, but had no effect at all on heteroscedasticity or on this QQ plot. Now the QQ plot indicates some curvilinearity among the residuals. I'm going to my trusty notes here because I want to be specific. There's a test that never gets used in my field that's actually should be used. It's called the SCORE test. And so what it does is statistically examine whether the variance of the residuals changes a function of the predictors. Right? So in the predictors here, we're talking about job satisfaction and absenteeism measured at another point in time. So the test involves regressing the squared residuals, these are the residuals, from the original regression on the predictors. And in this particular case, the SCORE test suggests that heteroscedasticity is not a function of the predictors. In other words, whatever is causing these residuals from the original regression to be different at different levels of absenteeism, it's not due to job satisfaction or other variables in the study. Okay? And this plot, the QQ plot, examines whether or not the residuals are linear or curvilinear, and the fact that we've got that bend right there, this is descriptive, suggests that there's some curvilinearity in the residuals. So I'm going to get to the bottom line in just a moment, but okay, I'll get to the bottom line right now. It's about a lot more than just is your variable skewed. Are the raw scores skewed? That's a very small piece of the picture. So in this example that I just gave you, the data are non-normal in a variety of ways, some of which are not evident from looking at the usual statistics, you know, that little table with the skewness and the kurtosis. Taking the log can reduce skewness and kurtosis, I mentioned this, but didn't have an effect on the other aspects of non-normality. So what that means, I think, is that the transformation didn't make the data any more suitable for OLS regression because the assumptions in OLS regression don't have anything to do with the skewness of the variables. It's about the residuals, and the transformation had no effect on the residuals. Does that make sense to you guys? Okay. And here's something else. Nonlinear transformations can change results, as I mentioned earlier, and that change in results isn't necessarily appropriate. It's not like the change in results necessarily reveals the truth. So the correlation between absence and logged absence was very high. I gave it here, 0.93. But in this case, log absence was not significantly associated with job satisfaction, while the original scores of absence were. It could have gone the other way, correct? And I'm going to say something sort of cynical here, guys. Let's say you've got assistant professor X. I'll be assistant professor X. And you happen to live in a world where if you don't publish, you lose your job. And you're gathered all this data and you're crunching the numbers, and it's like P is less than 0.12. It's killing me. Well, okay, you can either throw it all out or you can explore your data, right? And you know what? I'm not blaming assistant professor X about this. I mean, that's just the system we live in. So, you know, I thought it's the same kind of cynicism I had with regard for control variables. My suspicion, I'm not accusing anybody in the world, my suspicion is we live in a system where sometimes you'll have people throwing in control variables or removing control variables to get P less than 0.05. I think that happens. You could do the same thing with nonlinear transformations. So let's say this was reversed. You've got your hypothesis, job satisfaction leads to absenteeism such that more satisfied people are absent less often. That's your hypothesis. It's P, in this case, well, let's say the correlation is 0.063. It's the other way around, not significant, but you just miraculously take the log and now you got a significant correlation. So again, I'm not sure how often this kind of thing happens, but the cynical part of me just says, well, it's reality. I mean, you're saying, do you want to keep your job or no? So anyway, I'm glad we don't live in quite as brutal of a world here, but nevertheless, it could be that way. So where we're headed with this is we want to complete kind of the illustrations, the concrete illustrations, so that the paper serves as kind of a one-stop shop for people that are interested in conducting nonlinear transformations. And I think doctoral students for sure, but in my field, I think a lot of professors just, it's just become kind of a rule of thumb: skew, take the log, move on. And we can do better than that, I think, in my field. I'm really curious to find out how things are done in your field, or if it's even an issue. So I'd like to open the floor to questions, and certainly any comments you have about how things are done in your particular field or similar issues that you've faced. Yeah.
All right, so thank you very much. I was late like 10 minutes. I don't know, maybe you've already talked about it. We have very similar fields. So it's hospitality research, it's stuff from social sciences and stuff like that. So it's similar stuff. Well, I also work in statistics and social equation modeling and stuff. So there's a debate, and that debate is: are we only looking to have p less than 0.05, which you explained, right? So it's true, we have multiple methods and multiple techniques to reduce the skewness or whatever. Yes. But don't you think, just tell me your thoughts, that when you collect data and you have a skewed data, so rather than having something to reduce the skewness, try to understand why the data was initially, because you might have biasness in your data. Now we are talking about common method variance or response biasness, so stuff like that, especially in cases where you are asking the single source, let's say employees, about their absenteeism and their job satisfaction. So they may have a lot of bias there, which may result in skewness. Now, if we come up with a statistical method to reduce skewness, how about ethical considerations? Because now we are playing the data. So what do you think about that?
Yeah, no, I think that's a very good point, and there's certainly an inclination for people to explore the data in that sense. I think actually things are potentially getting better, because there's more options. Well, let me put it this way: more people are becoming aware of more options than used to be. So, as Bayesian statistics become kind of widely discussed in your area.
Oh yes.
Yeah.
Not widely, but it's getting some
little
sort of
attention.
like the top journal in tourism, which is tourism management. They are now moving beyond structural equation modeling, and they want you to have some sort of supplemental analysis like fuzzy set, qualitative, comparative set, or patient statistics, something which goes beyond E is equal to whatever.
Yeah, it's funny, isn't it? There's been philosophers of science, I think now for decades, have argued against that p less than 0.05 is arbitrary and in some cases misleading. Yeah. So I don't know a lot about some of these alternative techniques, but I know Bayesian techniques, partial least squared methods, right? A lot of these don't make the same kind of assumptions as OLS, ordinary least squares regression does. So the more of us that are kind of becoming familiar with that, I think maybe we can sidestep the use of these nonlinear transformations. At least, I'm not saying they're always bad, but I think we'll be able to make more informed decisions as we kind of get those other techniques under our fingers, so that we know how to use them.
Just one more thing. Is this a review paper, like where you review the usage of nonlinear transformations, or is it just an application, or what? The data from this were 323 articles that were randomly sampled from 6 of our premier journals. And so what we're looking for was simply to find out, being able to describe realistically, this is how nonlinear transformations are currently being used. Here's what's being done to justify them. Here's how they're being reported. Here's how they're being interpreted. Yeah. Sure, of course. Other comments, Melissa?
Just out of curiosity, so related to your thought that you expressed earlier, did you, among the things that you coded, did you code rank of the authors? Because if you did find anything about assistant professors in particular that were being a little fuzzy in their use of transformations, I think that says something different too.
Yeah. We did not. You know, in fact, we explicitly decided, and we say in the paper, we're not reporting any names or anything, because the goal isn't to say, oh, look, you bad person did this. Because I think, you know, my interpretation is to the extent that those questionable research practices occur, it's not that the individual's not at all responsible, but the system certainly is, in my view, more responsible. But at any rate, yeah, so we opted not to make an issue of that at all. We just focused on the statistical issues.
Yeah, and my other thought was, and you might be able to speak to this from your work on the control variables, but this is, I think, a critique of the editors and peer reviewers as well. So do you expect to hear anything from any commentary?
You know what we did with the control variable paper? I actually did a review with like 6 other colleagues, and it was published in 2016, last year. And we sent copies to the editors of our top journals. And one of our journals, the Accounting and Management Journal, has now adopted some of our recommendations as part of their editorial review policy. That, you know, if you're using control variables, we expect you to at least explain why. We ask that you report the results with and without the control variables and so on. So I think that was kind of gratifying, because if you just leave it up to, you know, if you just wag your finger at people or something, that doesn't have any effect. So my hope is that we'll be able to share the final version of this paper with reviewers and editors. Because a lot of times the reviewers aren't only innocent bystanders, they're part of the problems, you know. You know, have you tried this? Why did you do that? They kind of ghost write your paper for you. You know? So anyway. Now, what about in psychology? Do you see very much use of nonlinear transformations? I don't know.
Not within my immediate area, but yeah, certainly within psychology more generally. And I, like what Carlos said, I think so much of the time it's because so-and-so did it this way, or it's assumed that you use this transformation with this particular variable.
Yeah, I think, you know, the kind of the benign explanation, which is in many cases I think true. One of my colleagues, well, Bob Vandenberg on the paper, he's actually now got 2 books out on what he calls statistical myths and urban legends. And every chapter is written by somebody who knows something about a particular area. And it's basically why half the stuff you learn in grad school really is not quite true. When it comes to, you know, just always do this and just do that. So.
Yeah, but I come, of course, from engineering background, and in engineering they use a lot of nonlinear transformation, but as you have recommended, we have to always look and see why we are doing nonlinear transformation and if it can justify the cause. However, looking at statistical approaches, the thing that I have noticed about them is that they cannot work in both frequency and time. Usually you have to sacrifice one or the other, which means that you either lose coerced data or details, one way or another. But when you do, for instance, when you square your variables, basically you're losing coerced data, and then when you do log, you lose details of your information. So there are now some filtering techniques that can keep both time and frequency effects. However, again, I don't know how it can apply to your particular approaches for the nonlinear transformations, but basically the idea is that you decompose your data so that you would keep both the low frequencies and the high frequencies, and also the time effect. So I would be glad to work, because I have done some research in that area.
I'd like to learn more about that.
I would love to read your paper maybe and then see where the uses for nonlinear transformation and how we can apply these techniques to that sort of data to keep everything.
Yeah, because a lot of strange things happen when you start doing these transformations without giving a lot of thought to it. Like here's one example. there's a technique called Winsorizing. So let's say that you've got a variable that you want to transform, but there's a bunch of values on the original variable equal to 0, right? 0. Well, log 0 doesn't have a meaning. So people will add some small amount to make it non-zero, okay? And that sounds reasonable, but then when you take when you do that, and then you take the log of that whole data set, you've transformed a ratio level measurement to ordinal level data, right? So ratio level, you have a true 0, equal intervals between scale points, and now you've got no 0 and unequal distances between scale points. And this raises potential statistical issues because, for example, the F-test presumes ratio level measurement. In my field, we routinely ignore that as long as it's at least interval level data. But now you got ordinal level data. It's really unclear whether you should be using an F-test.
In fact, one of the methods that I'm familiar with is very much similar to music, and you are an expert in music. So the same way that you can represent your notes in 1/8 note, 1/4 note, 1/16 note, you can keep your data the same way. So you don't have to eliminate anything. You just put it in a different order. So you will still have everything, and you can keep track of everything, but still you can do your analysis.
All the information.
All the information is there. Just the way that you look at it is. So you, for instance, you could have 10 whole nodes, and then I don't know, 12 16th nodes, and so on and so forth. So that's a different way of looking at data.
Yeah,
I know you mentioned initially, but I missed the point perhaps. So you did not look at the dependent variable transformations, or you did?
We did actually. So in collecting the data, one of our coding categories was added an independent variable, dependent variable, and control variable, and we found, a significant number. Well, not statistic. We found a substantial number of each category. But if you listed out the total number of variables transformed, the largest proportion of all those variables was control variables. But there still were independent and dependent variables that were transformed. So I don't remember all the objections to transformations of the dependent variable, but I know that there are objections to that. It seems, I think it's because it's kind of for the same reason. About when it comes to interpretation, you're usually interested in explaining variance in the dependent variable. So now if you change the meaning of the dependent variable, you've lost kind of the focus of your study. I think that's one of the perspectives, but we didn't really get into that here.
My background is engineering, so looking at lots of experimental studies, that's where these transformations are applied. Of course, sometimes it's heteroscedasticity type of transformations, but sometimes we also have in experimental studies. Suppose if we are looking at a response that's continuous, typically supposed to follow a normal distribution, no issues at all. But if you're performing ANOVA, that kind of stuff, and you're looking at detective rate, it's expected to follow binomial distribution. So looking at what kind of distributions we could expect to see for the responses, statisticians have recommended certain types of transformations. And sometimes we count how many defects per unit or something like that. That typically follows a Poisson distribution. And various experiments by statisticians have shown that either square root of C or square root of C plus 1 type of transformations work. And over a period of time, what happens is people just take them for granted and then just blindly apply them.
Yeah.
That's what happens. But I don't know, So in your field, you have not seen application of finding out an appropriate nonlinear transformation in an analytical sense. So basically, you let your data drive what type of transformation probably could work for better or something like that.
Yeah, so I don't see much of that, and I'm just thinking through your last comment about letting the data drive. I see some benefit to that, and I also see some danger to that, because in any given study, some of what you're seeing is chance. So if you don't have, obviously we're suggesting you take a close look at your data before you just start kind of blindly taking logs and assuming that's going to fix things. So for sure that's consistent with your basic notion. Yeah, but in my field, I think it's just as simple as most people have the rule of thumb. If it's skewed, take the log, and then hopefully the reviewers won't give us a hard time about it. I really think it's pretty much that simple. Because that's the explanation that you get in 88% of the cases is X was skewed, so we took the log.
And quite a bit of discussion you find very little in some of the books. Design and analysis of experiments, Douglas Montgomery, and of course the older statisticians too, which topics are discussed.
We've done a book by Cohen, Aiken, and West that had a pretty good discussion about nonlinear transformations that I've never seen cited. So Bob Vandenberg said, "Hey, there's this section, section in the chapter on nonlinear transformation," and we drew from that pretty heavily in some of our discussion. So it's not like it's been totally ignored. It's just been widely ignored by contemporary researchers, I would say, in my field.
One of the issues is typically these things are not really taught in most of the places,
That's right.
Even to the graduate students. Perhaps they're not even aware that such things need to be looked at when analysis is performed.
At Ohio State, they didn't have, we had to take if you wanted a minor in statistics, you had to take 6 courses. And the first 3 everybody had to take anyway. But I took a course in exploratory data analysis where we used Tukey's book. But that was offered as an elective, and only because there was a visiting professor there who wanted to teach the class. So it wasn't part of any systematic training. Had that guy not been there, I would be totally ignorant on the topic too. So. Too long here. It's almost 3:30. Other questions, comments?
Okay, so do you think type of the variable may have any impact on the transformation?
Tell me what you mean.
Like, for example, you have multiple types of variables, right? So if you have a categorical variable, would that differ as compared to a finite variable or something else? So do you think, or have you ever looked into that? Something like that?
Well, I think the notion in almost every case that I've seen in my field is that it makes sense to take, well, the authors would argue it makes sense to make a nonlinear transformation of continuous ratio level or interval level variables. If you've got like a dichotomous variable, I'm not even sure. Anurag's not here. I'm not even sure what happens if you got 0, 1, and you take a log of 0, 1. Well, you can't have log 0, so you add something to it. You add 1 to it, and it's all 1. Then you don't have a variable anymore. It's a constant.
Yeah, so related to this, earlier you were saying multiple methods. I use partial least squares. Yeah. And for a lot of you who want to use that, what they do is instead of transforming, they standardize the data.
Yes.
So no requirements for normality or whatever, because the data is converted into zeros and ones.
Right.
So that's another alternative.
It is. Yeah, just a quick aside since you mentioned that winsorizing again. One analysis that Melissa Robertson, the second author on this paper project, did was she looked at, okay, so winsorizing is you got a 0, you want to take a log, so you add a little bit to it. The distribution varied pretty dramatically depending upon if you added like 0.1, 0.01, or 1. And when you think about it, that's a little bit arbitrary. You know, how much do you add? Well, whatever number you decide is going to have a considerable impact on the nature of the transformation. Yeah, Carlos?
What I'm saying is you add 1 to every value. Basically, you transform linearly the distribution first, and then you impose the nonlinear transformation. That way.
So 0 becomes a 1, and then you just add a 1 to everything else. That would make sense.
Now, one thing you mentioned about is, let's say when we transform the response and perform the analysis. And so when we use that for prediction, how do you interpret the response, right? However, we can always transform the transform variable back into the original form, right? So what kind of issues do you come across?
Yeah, let me just, I know we're almost out of time, so let me just share this with you, because that was something we had given some thought to. I'm going to try to find we actually had a little example here of that in the paper. So let me just read this to you. Even under the best of conditions, there's reason for researchers to be cautious when interpreting results that involve NLTs. So we recommend early in the paper, if you're trying to interpret the results, it's a good idea to transform it back. But the point here is even that only accomplishes so much. So let me just say this. Bob hypothesizes that X is positively associated with Y. He collects data on both variables, and during pre-screening notices that one variable is moderately positively skewed. Imagine that at that point he calculates a correlation between X and Y. All right, he calculates a correlation between X and Y. Then he does has a justifiable decision and takes the log of X. Post-transformation analysis showed that the log was effective in normalizing the distribution, etc. Bob then calculates a correlation between X and log Y. X and log Y. Okay, but then when you transform that back, you're still testing the hypothesis that X affects log Y, not X affects Y, right? So you've got the right metric of measurement in the original units, but it's not testing the hypothesis that you originally posed to test. You see the difference there? Yeah, so I've got a more specific example there, but yeah, we like the idea of transforming it back, but you still can't claim that you're testing X affects Y. It's still become kind of exploratory because it's log Y. Okay, guys. Happy to send you the paper when it's done if anybody's interested or talk more about possible issues and collaborations. Thanks all. There's some donuts left. Thank you, Gidi, for leaving some donuts.
That's a good question.
Thank you. Enjoyed it. Yeah, thank you.
Yeah, yes, and then he says, well, if he comes to the conference, I guess. This is